Hi, here we've got a really rare piece of vintage electronics. This is the DC-DC converter for my electric car, which is a 1988 Soleq Evcort based on the Ford Escort. This takes high voltage DC from the traction pack and converts it to 12 volts to run the lights and all the other 12 volt accessories in the car. So basically, it takes the place of what would be the alternator in a gas vehicle. So the input is 108 volts, which is the traction pack, and it converts that to 12 volts for the battery and the accessories. It's hermetically sealed in this aluminum case because it's used in the vehicle and just to keep it protected from the elements. Not really very much information available on this, no schematic or anything. Pretty much only what we can read on the label here. And that tells us that it'll take a DC input of anywhere from 75 to 130 volts. And it also needs a sync drive, 400 hertz, 110 volt square wave. And this comes from the main motor controller of the vehicle. So it's a switch mode power supply. Rather than having an oscillator inside the converter, it takes the signal from the motor controller, which is also 400 hertz. Of course, 400 hertz is a really low frequency for a switch mode power supply. Modern power supplies would have at least 50,000 hertz switching frequency, and that was just due to the limitations of the electronic components available at the time. So this worked when I got the vehicle, and then about 10 years ago, it just stopped working. I didn't try too hard to fix it. I bought a modern DC-DC converter, and I'm using that now. But I've always wanted to get this old DC-DC converter working again. So let's try to get it apart here. So we're going to pry this open here. Okay, let's see what we've got. So these are obviously the powered transistors. There's 20 of them, probably wired in some kind of parallel arrangement. There's a big honking transformer, probably the transformer that transfers high voltage AC to low voltage. And this looks like some kind of choke, probably a capacitor here, and looks like this is going to the outputs. Because I'm actually pretty sure that this is a center tapped winding here, but let's just check that with the LCR meter. And I'm not sure how much inductance we expect here, but let's just try this. That's the 2 millihenry setting. So green to white that'll be 400 microhenries. Green to blue, 400 microhenries. And then if we go from white to blue, 1700 microhenries. Okay, so these definitely are in series then. This is the center tap. And you expect this to be more than the sum of the two, since both coils are wound on the same core. Okay, so definitely a center tapped winding there. Okay, so looking at this circuit a little bit more carefully, see that this green wire, it's the same green wire coming up here to the capacitor and then going down. Again, same green wire. There it is. Going into the output cable. And then that's connected to the negative terminal of the battery connector. And then this blue and yellow wires, each of those goes down to what looks like a stud diode. And the other side of the diode is connected to this bar. This bar is connected to this red wire, which goes through the choke to the other terminal of the capacitor. And then that goes through this shunt here, which is probably to measure the current coming out of the converter. And then that is going down to this fuse. This is a 30 amp fuse. And again, that's going to the output, the black wire, the positive side of the output. Okay, so the low voltage side of the circuit is pretty clear. It looks like a center tapped winding here. Full wave rectifier going through the choke, capacitor, current measuring shunt to the fuse to the output. So now if we look at the switching circuit, these are TO3 style transistors, which you don't see much anymore, but which was once a very common case style for high power transistors. And I don't know if you can read it there, but it says OHBA, OHBA. That's Shunjiro Ohba. He was the designer of this of the vehicle, designed all the electronics for it. So these may actually be custom transistors. And certainly nothing there that looks like a standard transistor type number. Okay, so now if we look at these actual switching circuits, what you can see is under the plastic here, several what look to be high current bus bars, presumably connecting these transistors in parallel. There is also a number of low value resistors, 0.12 ohms. And those are often used to try to balance the load, make sure no one transistor carries too much of the current. Now I should mention that what happened 10 years ago was stop putting out DC current. I did take it apart, and there's a fuse on the 108 volt input, 10 amp fuse. That fuse was blown. So I put in a new fuse, plugged the unit back into the vehicle, and I found that this resistor got very hot, and then the fuse blew again. So just as a wild guess, I thought maybe I'd just disconnect this resistor. Maybe this was going to one of these transistors that was shorted, for example. So I disconnected it, put a new fuse again, plugged it in, and the fuse blew again. So that didn't fix it. At that point, I sort of gave up for the time being. But anyway, my hope is that I can reverse engineer these switching circuits enough to figure out what went wrong, and hopefully the problem is in the final switching circuit here, not in these more complicated regulatory circuits. Maybe find the bad components here and replace them, get this thing working again. So that's kind of my strategy. So these TO3 transistors, they have a very common convention, and that is that these pins are slightly offset, and if you have these toward the top here, this is the base, this is the emitter, and the case is the collector. So we ought to be able to go through here and trace out exactly what the circuit is. You can already see that these collectors are all wired together directly onto a bus bar, and the same with the thing with the collector of the transistors on the bottom. Then you see these lighter bus bars, and they're actually going to the base of these transistors. So that's presumably the switching signal coming in. Now some of these are divided between the right and the left bank of the transistors, and others of them seem to go the whole way across. So it seems like there's really four banks of 5 transistors each. Each of those are running in parallel. Now we can see a number of wires coming into the board, and actually some of those are labeled. So here's a couple of wires labeled T1 and T2, and you'd think that might stand for transformer. So maybe this is the primary of the transformer. So to check that, we've got the LCR meter here. And I'm just going to try to test what I think is the transformer in circuit here. So here's T1. There's T2. And that's reading 8 millihenries, much higher than the secondary, which is what you'd expect. So I can't really see where the wires go. So to determine if that's the same transformer, I'm going to short out the secondary here. And measure it again. There's T1, T2. Ha! It's going from 8 to 0.09. Okay, so clearly that's the same transformer. This is the primary, and that low voltage circuitry is coming from the secondary of the transformer. Furthermore, there's another wire here labeled POS. That's presumably the positive power coming to the board. So we can check that. Switch this to measure resistance. And I'm going to connect one lead to the fuse from the positive high voltage power coming in to this, and okay, so that's a short circuit. So that's directly going to the positive terminal of the 108 volt input. And that's going directly to this bus bar, which is connected to, looks like, all of the transistors on the bottom row here. Okay, so we have a lot of clues now to try to trace out this circuitry. But another thing we can do is try to check the transistors here using the diode setting. Now I don't know if these are PNP or NPN, but we do know where the base and the emitter and the collector are. So let's just try base to emitter. .4 base to collector. 0.4. And in reverse direction. Base to collector, open circuit, base to emitter, open circuit. So that looks like an NPN transistor there. Of course, we're measuring it in circuit, but I think several transistors wired in parallel is basically going to look like a single transistor. So I think these are all NPN up here. Anyway, now the ones on the bottom, these are inverted, so the base is on the right here. So again, let's go base to emitter, 0.4 base to collector, 0.4 in reverse direction. They're both open circuit. So it looks like these are NPN too. So I'm kind of assuming that all of these are going to be NPN. But let's look at this one, which is the one that I disconnected because it seemed to overheat the resistor. So this is the resistor going to the emitter. Let's go base to emitter. And that's a short circuit. There's nothing else connected to this emitter as far as I can tell. So that really looks like a shorted transistor there. Let's try the ohm meter scale. Okay, same thing. That's a dead short. And then base to collector. That's a short circuit too. Okay, so I think this transistor is probably shorted out. Let's try another one in the same bank. Base to emitter. 0.37. So that looks like a normal junction. Base to emitter. Sorry, base to collector. That's a short circuit. Of course, these bases and the collectors are both connected together. So if this was shorted, this is going to be shorted as well. But remember, I disconnected the emitter. So this is, so this would be separate from the shorted transistor. Let's try the other direction. Huh. 0.5. So that's neither, it's not the same in the reverse direction, but it's not an open circuit either. Of course, there could be something else in the circuit causing that that conductance rather than the transistor itself. But before we go, let's try some of these transistors on the bottom here. So this is base to emitter. That's a short circuit too. Base to collector, short circuit. So either this is shorted or one of the other transistors in the bank is shorted. Let's try another one up here. Base to emitter. .054. So that's neither a junction nor a short circuit. Let's try that on ohms. Ah, 54 ohms. Base to collector. Okay, short circuit. So that's kind of odd because the bases are all connected together, and the emitters are all connected together through these very small resistors. So how can this be a short circuit, and over here it's 54 ohms? Let's look at some of these resistors. Okay, that looks good. That looks good. Ah, this resistor's gone high. This is 54 ohms. So that's probably the 54 ohms that we've been reading on all these transistors. Okay, so I think before we go any further here, I'm going to try to trace out these circuits more carefully, try to figure out what's going on and why we're getting these shorted and very odd readings. I've managed to trace out the main power circuits, and here's a schematic. There are 4 banks of 5 transistors each wired in parallel, but to simplify things, I've drawn just 2 transistors per bank. It turns out to be a pretty standard H-bridge inverter that converts DC to AC. On 1/2 cycle, pulses from the driver board turn on the upper left and lower right transistor banks, so current flows from the 108-volt source through the upper left bank, rightward through the main transformer, and through the lower right bank back to the source. On alternate half cycles, the upper right and lower left banks are turned on, so current flows leftward through the transformer. The transformer steps down a resulting 400 Hz alternating current by about a factor of 5, and the lower voltage AC is converted back to DC by a full wave rectifier. Of course, all of this has to be regulated in a way that keeps the output voltage at 14 volts, despite variations in input voltage and wide variations in output current. So what happens if you have a shorted transistor, for example, in the lower left bank? When the upper left bank turns on, that opens a short circuit directly across the DC supply, blowing the fuse. 10 years ago, when I discovered the hot resistor and disconnected it from the emitter of the shorted transistor, what I didn't realize is that current could still flow from the collector to the base of the bad transistor, then through the bases and to the emitters of the other transistors in the bank, again completing a short circuit when the upper bank cycles on. So of course it still blew the fuse. But now if I just disconnect both the base and the emitter of the 2 shorted transistors, then the remaining transistors in the bank should function normally, and I should be able to operate the converter as long as I don't load it too heavily. Okay, so I think what I'm going to do is disconnect completely these two transistors that we know are shorted out, and then measure the junctions of the remaining transistors in the bank. And fortunately, that's easy to do because for the emitter, we can just disconnect the associated resistor. It appears there's nothing else connected to the emitter. And then for the base, that's connected through this little jumper that we can simply disconnect. So I wouldn't have to really remove physically any of these transistors. Finally, this jumper is labeled R3 as if maybe in an earlier design, maybe they had a resistor there and then decided to eliminate. But anyway, I'm just going to disconnect these two transistors. Okay, so now I've disconnected both of these resistors and both of these jumpers to the base connection. So now these two shorted transistors are completely disconnected from the circuit. So let's then recheck these junctions. Base to emitter, 0.4, base to collector, 0.4. And reverse direction, open circuit, open circuit. Let's do the lower bank. Positive on the base, base to emitter, 0.4, base to collector, 0.4, and reverse direction, open circuit, open circuit. Great, so it looks like the remaining transistors in both of these banks are still good. So here we are at the car. I've made up this little dongle. This is the cable from the controller. It goes to an Anderson connector. So then this adapter turns this into a normal extension cord plug, and then I just use an extension cord to take this into the house. Okay, so I've got the controller in the car switched on, and just going to take the test the input sync signal here. So here's the extension cord from the car measuring on this voltmeter. And it's 112 volts AC. Incidentally, I found you have to have a true RMS voltmeter because it's a square wave. Otherwise, the voltmeter goes crazy. Okay, so I think we're ready for a test here. I've made this complementary dongle to take the sync signal from my extension cord and then splice that into the Anderson connector to the converter. And then for the DC supply, I'm using this old laptop computer power supply. It's just the rectifier bridge and the condenser, and feeding that with variable AC from a Variac. And just to make sure we don't have any grounding problems, powering that with an inverter and some batteries upstairs. So that'll be our variable DC supply. And then instead of the 10 amp fuse, I spliced in a smaller 2 amp fuse just to make sure we don't do any damage. And I've got 3 meters here. So this is going to measure the input DC voltage to the converter. This will measure the output voltage. And I've got a clamp DC ammeter. This will measure the current going into the converter. So let's just turn these on. Okay, so to start, I'm plugging in just the sync signal. It's already humming, and it's already accumulating output voltage. Didn't expect that. Seems to be leveling off at about 4 volts. Let's get this on the right scale. Okay, I'm going to turn on the variac here. 12 volts is not going to do much. Let's turn it up a little. Okay, so 32 volts. We're already up to 7 volts output. 1/10 of an amp input. Actually, the minimum voltage to use is supposed to be 70 volts. Let's bring it up some more. Okay, 50 volts, we're up to 12 volts output. And it's not blowing a fuse yet. 14 volts. And you could hear the change in the hum, that it's obviously regulating the output here. And we're up to 70 volts. Of course, that's without any load. For load, I've got a turn signal bulb here. That takes about 2 amps. And let me just connect it here. Well, that's dropped the DC input voltage. So this little power supply is already getting taxed. But it seems the converter is actually working pretty well. Just see if anything's getting hot here. Forgot to mention I've disconnected completely the two shorted out transistors. Everything still feels pretty cold. Not really taxing anything here. Okay, let's just raise the voltage a little bit more. Make sure it's still regulating. Okay, 90 volts. I think for now I'm going to stop here and figure out what to do next. But it does seem to be working. At least it didn't blow a fuse, which is what it was doing when I started. Okay, so I think we're about ready for a test at full voltage here. And rather than use a variac, I decided to use the traction pack from the car. So I've got another cord running up all the way to the car, bringing in 118 volt DC from the battery. And here that's coming out here. I've got a couple of resistors here so I can put those in a line. And then that goes through the same 2 amp fuse into the positive input of the converter. And then I got the same meters set up. Again, this is going to be the output voltage. This will be the input voltage. And this is going to be input current. So I'm going to plug in the 400 hertz sync signal. So this is coming up to about 4 volts, just like it did before. Okay, let's connect the DC I'll connect it through a 500 ohm resistor here just to be sure something crazy doesn't happen. So the input voltage looked a little bit unstable there for a while, but now it's gone up to 118 volts. This is still regulating at 14 volts, so that's good. Amps has gone down to 0. Okay, so it can regulate at full input voltage. Well, I'm going to go connect it straight to the 118 volts. Still regulating. Okay, let's put on the load. Oh, well, the output voltage is very stable, but the input voltage is going crazy. But the current is very steady at 1/10 of an amp, which is about what it should be. But there's a noise in here. Sounds a little bit like a sparking. Seems to be kind of down in the center there. I thought maybe the transformer shorting out, but actually doesn't sound like it's coming from the transformer. Sounds like somewhere down in the bottom there. Now this voltage, I don't think it's really varying that much. This is connected directly on the line from the 118 volt source. But maybe this thing is inducing an AC signal, messing up the detection by the meter. Let's just try this other meter. Switch to volts. So on this meter, which is I found more tolerant to noise in the signal, this is reading a steady 118 volts. So I think that's really the correct voltage, but I guess there is some noise in the line. And I really don't like that noise. Don't smell anything. So I think maybe I'll just shut this down and try to figure out what to do next. Okay, I'm still worried about this noise because it sounds sort of like something sparking. I don't see any spark, but it seems to be coming from somewhere down back in behind this circuit board. It's hard to see anything back there. So I'm thinking maybe I can unbolt the board and run the converter with the board flipped up out of the way. Maybe then I could tell exactly where the noise is coming from and whether it's really a problem. Okay, let's see if we can get this circuit board loose. You have to cut these zip ties. Get enough slack in the wires. Okay, so I've been able to detach this circuit board with all the high power switching circuits on it. And I didn't have to remove any of the wires. So I think we can run this as it is without any problem. So I've got the same setup as before, running it off the traction pack in the car with the 400 hertz signal from the car. And this meter is going to measure the output voltage. And what we want to see here is, does it still make that funny rattling noise, or was that some problem with maybe shorting of these transistor cases to some circuitry down on the bottom here. Or if it does still make that noise, maybe you could tell where that noise was coming from, which was kind of difficult to tell when it was all together. Okay, so I'm going to plug in the 400 hertz signal now. And just as before, we can see this coming up onto about 4 volts. And then it levels off there. So now I'm going to add the DC input, 108 volts, and I'm adding it here through a 500 ohm resistor. Okay, so you can see all this almost immediately comes up to about 14.3 volts and then stops there as the regulation kicks in. So now I'm going to go ahead and connect the DC directly to the input. Voltage overshoots a little bit and then gradually comes down. So now I'm going to add this 1/2 amp load. And as you can see, it maintains the voltage pretty well, but it is making that noise again. So it apparently wasn't anything to do with shorting of the transistor cases. In any case, they're pretty well separated now. But now that I've got this apart, it's really clear where the noise is coming from. It's definitely coming from this choke, the filter choke on the low voltage side of the supply. So why is it doing that? Well, to help diagnose that, we're going to look at this on an oscilloscope here. So this oscilloscope, I've powered it from an inverter and some batteries so that we can avoid grounding problems. So the ground here is connected to the minus side of the DC input through a 500 ohm resistor, which shouldn't affect anything. And then I'm going to touch this probe to the base of one of the transistors. So this will be a transistor on the lower bank, the bank that's connected directly to the minus rail. And what we see here are irregular pulses. So to try to sync this, I'm going to switch to DC coupling here. And you can see pretty clearly that the pulses do match the sound coming out of the choke. Now let's see, this is 1 volt per division. This is on a 10x probe, so it's really 10 volts per division. So crank this up to 0.1. This is about 1 volt per division. So you can see it's making very short pulses here. This is 1 millisecond per division. So half of a 400 hertz cycle would be 1.25 divisions. So this is much less than that. So it's not even turning on for a full cycle. But anyway, what I'm starting to think here is that this noise is not necessarily a malfunction, but it's just this choke responding to those pulses as this thing turns on and off intermittently. Now, why does it turn on and off intermittently? Well, there are several ways you could regulate the output of this unit. If it's on all the time, the voltage is going to way overshoot. So you have to regulate these pulses. Now, you could just regulate the pulse width, but if you think about it, we're only drawing half an amp. This unit is capable of putting out supposedly 40 amps at 14 volts. So that's really like 1% of the rated output. So I don't think you could really put in a pulse of that short duration, that is one hundredth of a cycle. So instead it must have some additional mechanism that turns it on and off in order to support these very small loads. So again, I'm starting to think maybe there's really nothing wrong with this, that it just makes that noise when you apply a small load. So I'm going to change this now and put on a slightly bigger load. So this will be a 2 amp load. This is the turn signal side of that same bulb. So let me switch it here. Okay, so now we're getting basically the same thing, but just more frequent pulses, which certainly makes sense with about a 4 times stronger load. Now I've tried to look at what happens to the collector, and seems to just kind of bounce all over the place, and I can't really interpret that. Not sure what's going on there. But as far as the input pulses, really seem to actually make sense now. So again, starting to think that maybe this is just how it sounds with a small load. Okay, let me take the load off. I'm going to turn off the voltage here. So just checking over the unit here, there's really nothing overheating. There's nothing really heating up at all that I can tell. So really no sign of malfunction other than that funny rattling noise. Otherwise it's regulating the voltage well, it's providing power quite well. I have a little ammeter here. It's not drawing excessive current from the DC source. So again, I think maybe this is operating okay. I'd like to try it at a higher load, maybe closer to its capacity, but I'm reluctant to do that while we still have these shorted transistors disconnected. So I think the next step is to get some transistors, restore all 4 banks to 5 transistors each, and then try a little bit higher load on this thing. So stay tuned, and thanks for watching.